Alright, last video we learned about charge, and we discussed the need for there to be another long-range force, and today we are going to discuss Coulomb's law, which is essentially how we quantify the amount of electric force that exists between two charged particles. And so if you look at my picture here, I've got two charges, Q1 and Q2, separated with a distance R12. And we use Coulomb's law to calculate the amount of force, right, the repulsion or the attraction, between these two charges separated by that distance. And so Coulomb's law I have written out right here. And if you look at just the pieces that are in this orange box, you'll notice that it looks an awful lot like the universal law of gravitation. This force, this Coulomb force, depends on the amount of charge in particle 1, the amount of charge in particle 2, and then the distance or the separation between those two objects. So very similar to gravitation. And then the other thing that's similar to gravitation is that there is a constant term out front. All right, so let me get rid of some of these marks. So the constant is 1 over 4 pi epsilon naught. So epsilon naught is referred to as the permittivity of free space. That is equal to 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. And again, that's the permittivity of free space. Now, sometimes you will see, instead of 1 over 4 pi epsilon naught, sometimes you'll see that written out as K. So the whole thing, 1 over 4 pi epsilon naught, treated as the constant. And if you put those terms together, K is equal to 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Right? And that's referred to as the electrostatic or the Coulomb constant. Either way, it just goes out front of our Coulomb expression. Again, the Coulomb force law tells us that the force of attraction or repulsion between two charges is proportional to the product of the charges themselves and inversely proportional to the square of the distance or the separation between the two charges. Now, what I've highlighted in orange is just the magnitude of the Coulomb force. What's the direction? Well, the direction is along the line that connects Q1 and Q2. And if your two charges are unlike, then that force will be towards the other charge. And if your charges are like charges, then that force will be away from the other charge. All right, so let's look at example 5.1 just to do a quick calculation. We are going to find the force on the electron in a ground state hydrogen atom. The ground state hydrogen atom, there's a separation of 5.29 times 10 to the negative 11 meters between the proton and the electron. So go ahead and pause the video right here and solve this on your own, and then when you're done, unpause it and follow along as I finish the problem. All right, so pause it now. All right, so if we want to find the force between two charges, we're going to use the Coulomb force law. And in this case, Q1, we'll call it my proton, is equal to plus E. So that's 1.6 times 10 to the negative 19 coulombs. And Q2 is minus E, minus 1.6 times 10 to the negative 19 coulombs. And we've been given that R12 is 5.29 times 10 to the negative 11 meters. And so I'm just going to plug in the numbers here. My 1 over 4 pi epsilon naught, remember, is 9 times 10 to the 9 Newton meters squared per Coulomb squared. That was the electrostatic constant that I put up there. Then we're going to multiply by 1.6 times 10 to the negative 19 coulombs. 1.6 times 10 to the negative 19 coulombs. And then we're going to divide by 5.29 times 10 to the negative 11 meters. And we got to remember to square that. All right. And so there's a variety of ways that you can multiply this all out. But now I've got all the numbers in there. Really, it's just a matter of using a calculator. And so multiply all that out. I end up with 8.25 times 10 to the negative 8 newtons. And again, this is just the magnitude. If we want to talk about the direction of the force on the electron would be towards the proton, or towards the center of the atom. And that is the force on the electron in a ground state hydrogen atom. Okay, so the Coulomb force law allows us to calculate the force of repulsion or attraction between two individual point charges. And so the obvious next question is, well, what if there are multiple charges that are repelling or attracting your charge of interest? And so that's what we're going to look at here. A few things to point out before we get started. There's a distinction in electricity between source charges, that are the charges that are providing the pushing or pulling, and our test charge, the charge that is being pushed or pulled. And so let me just point out here, I've got I've got 8 different what I'm calling source charges, and I'm circling them. And these source charges are charges that are not interacting with each other. Now you can think of them, and I've got it written over here, put a pin in it. You can think of these source charges as stationary. They've been pinned down, they've been fixed in space. So their presence does not affect each other, right? So these source charges are static. This is why this chapter is known as electrostatics. Our charges, our source charges are fixed. They cannot move. So I've got 8 different source charges in this figure from the book, and then I have one test charge. So that's this charge right here. This is the charge that I'm interested in finding the force on. What is the force on this charge due to the presence of these 8 source charges? All right, so that's what we want to think about. And since Coulomb force law, force is a vector, if we want to figure out the force, the net force, we've basically just got to add up each individual force, and that's what I've got written right here. I've got 8 different source charges, so I'm going to want to add up 8 different terms. So the force due to source charge 1, the force due to 2, etc., 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 all the way up to charge 8. Right, so that's my objective. And in the next line, you can see I'm writing out each of these terms. And you'll notice something, if I zoom in here, you'll notice something that each of these terms has a big Q over 4 pi epsilon naught. And so what I can do is actually factor that out and rewrite the sum in shorthand notation right here. And so let's go through what this means. So the summation sign right, is just a shorthand way to write out those 8 different terms, or now I'm generalizing to the n different terms. And so I varies from 1 all the way up to 8 or 10 or however many source charges you have. And for each of those terms, you're going to look at the charge associated with that object, the separation from your test charge to that individual source charge, and then the last thing that's in here is the term that carries the vector, the direction nature, this r hat, and I've got it written out over here. This direction vector points from the source towards the test, and you can see in my figure up here that each of these lines represents that direction. Those arrows are pointing towards the test charge, so from the source towards the test. And if we want to add up the net force, we have to add up each of these individual vectors to find the net or the total force. Okay, and the easiest way to demonstrate how to calculate the net force due to multiple source charges is to look at an example. So I'm going to work through example 5.2 from the book. I would recommend pausing right now and trying to work through this on your own. And then when you're done, unpause and follow along. Okay, so first thing, let's just look at this image that's provided and let's identify our source charges. So we've got 2 source charges here, and we've got our test charge, Q2, that we're interested in finding the net force on. All right, so the book has already sketched out the individual force vectors. So this force vector right here, this F23, that is the force on 2 due to the fact that charge 3 is located in the problem. So in this particular problem, Q2 is negative 3e, and Q3 is negative 5e. So those are like charges. So the force on 2 due to 3 is repulsive, and that is why Q2 is getting pushed to the left from Q3. Now, we've also got force 2-1. Now that is the force on 2 due to the presence of charge 1, and charge 1 is positive. And so the force on 2 will be attractive, and that means that 2 will get pulled up towards charge 1. So those are my 2 individual force vectors, and of course we know from 101 we can add those 2 vectors together tip to tail to sketch out what that net vector looks like. Right, but we don't just want a picture, we want a quantitative magnitude and direction for this force, and that's where the Coulomb force law is going to come in. Now, the thing to realize is that our force 2-3 is along the x-axis, and our force 2-1 is along the y-axis. And so when we go to set up our Coulomb force law, we're going to find these forces individually, and then we're going to add those vectors together the way that we know how, using essentially the Pythagorean theorem. All right, so I've already sketched out some of this work, and so we're just going to sort of go through it together. So the first thing, I'm going to calculate F2 on 1, and I've sketched out what that looks like, just writing Coulomb's law, and notice that I've included the direction here, the j hat direction. That's the plus y direction. That's the up direction in my picture. And if I plug in the appropriate numbers, I end up getting that the force on 2, due to the presence of charge 1, is 3.46 times 10 to the negative 14 newtons, again, in the j hat direction, in the upward direction. I can do the same thing and calculate the force on charge 2 due to the presence of charge 3, and that's what I've got written here. Notice my force on 2 is to the left. That's my negative x direction. That's the negative I hat direction, and that's why I've included that negative sign. Plug in all the numbers. End up with a force on 2 due to the charge 3 with 2.16 times 10 to the negative 14 newtons, again in the negative I hat direction, the negative x direction. So I've got these two vectors. I need to add them together. Of course, we're going to be using the Pythagorean theorem. So I'm plugging in those numbers. And I get a magnitude for the net force of 4.1 times 10 to the negative 14 newtons. Now I also need the direction, and so you can see in this picture, I've already defined the angle theta as the angle above the negative x-axis, or the angle clockwise from the negative x-axis. And so I can write out the tangent of that angle is going to just be the ratio of the y component divided in the x component. And so I can solve for theta just by doing the inverse tangent, and I get 58 degrees, which allows me to write out the net force on my charge 2 as the magnitude, 4.1 times 10 to the negative 14 newtons, and then the direction, 58 degrees clockwise from the negative x-axis. And that is the answer to this particular problem.